Hi, I am Rajneesh Sharma, and today I'll be presenting my master's research project, which is scaling of soil organic carbon in space and time in southern coastal plains. I am doing this project with Dr. Matt Levi at Department of Crop and Soil Science at the University of Georgia. So soil organic carbon is one of the most important soil properties, and it's not just important for soil health, it's also a big part of global carbon budget. Carbon sequestration is one of the most feasible way to reduce the concentration of atmospheric carbon dioxide. That's why observing and monitoring soil organic carbon stock is important. But the scaling of soil organic carbon comes with its own constraint. It's mainly because of the sampling capabilities, because um, the number of samples we can take by going to field are limited, and and then there are scaling constraints. So right now, USD and NRCS use land resource hierarchy, a simpler version of land resource hierarchy shown on the right. So first, soil scientists take sample from soil profile, which they analyze in lab and come up with the carbon value to it. And a number of soil profiles get clubbed together to represent a soil map unit, which is mainly look like this in a county, and number of map units are clubbed together to MLRA. So MLRA 133A is our study site, which spans over 9 states in the Southeast United States, and it's the largest MLRA in United States. MLRAs are major land resource areas, which USDA divides US to make the strategy and policy making for soil conservation uh, easier. So the problem with the scaling hierarchy, which is land resource hierarchy, is that it's just spatial and it fails to capture the temporal aspect of changes in soil organic carbon. It doesn't represent how it will change in time, and it's fixed for each time. And so, a theoretical concept to solve that is ecological site and state and transition model. But this ecological site and state and transition model is not established in Southeast United States. So that's why and the state and transition model is just conceptual model. So that's why we have to find a way around, which I'll discuss in methods, how we'll do that. So ecological sites are sites with the similar potential to support vegetation and ecosystem, and so they represent similar soils, so they classify an area like based on their similar precipitation, similar temperature, similar parent material as a similar soil type. And within those similar soil groups or soil types, there are changes occurring which are recorded in state and transition model. So there are different states in an ecological site which transit into each other in time. So it may be like a natural forest at some time, and it may change into planted pine, pasture land, or cropland within each other, depending upon time. So these all affect the soil organic carbon and distribution over spatially and temporally. So this is how a spatial state and transition model records its states. So as I told, like it's just a theoretical model and it's not spatially defined. That's why we can use National Land Cover Database to define it spatially. National Land Cover Database is a 30-meter land-based database which is released every 5 years from 2001 to 2016, and these classes in the land cover can be used to represent the states of state and transition model spatially. Like first four classes here are some types of forest, which we have like three classes in land cover legend, which is deciduous, evergreen, and mixed. And crop and pasture can also be represented by pasture or cultivated crops. So challenges, soil and organic carbon is time and labor intensive to collect. That's why most of the efforts are project specific and end up having clusters of data at some special research stations. And the temporal aspect, like the frequency of those points taken over time also is non-uniform. So this picture shows like how in 2002 and 6 there were like very less soil organic carbon points, and then we had like a little more number of points in 7 and 11, and then again they decrease. So this creates a problem to actually scale carbon stocks for different time periods. So to solve this, we come up with a strategy, which is we call DSP scale model. So we divided our research into three phases. First was strategy making. So for strategy, so ecological site and soil taxonomy both captures the spatial aspect of soil organic carbon, like how it's distributed over spatially, and the for temporal aspect we will be uh, including the changes of land cover, like land cover from two different time periods, and changes between them will be representing uh, the temporal aspect of changes in the soil organic carbon. So second phase of this research was data collection and its standardization. So we are using these data resources. These all account for pretty much like 1400 data points, which we'll be using in our model. So first, we calculated carbon stocks for all those data points, standardized them for first 20 centimeter. That's the depth we'll be using. We'll be measuring the stock for, and then we tied up a land cover for particular time period. So all the points between 2004 to 2008, their current land cover will be like associated with 2006 conditions, and for 9, 13, 2011, and respectively 14 and 18 will be represented by 2016. So for the actual modeling part, which is our uh, third phase of the research, so we are considering two types of covariable, one which shows the spatial distribution of soil organic carbon, and the other types is like which shows the temporal distribution. So this is the point where our research have an edge over the other spatial studies, because we are considering the temporal aspect of uh, distribution, which other studies do not consider. And this gives us a leverage that we can make. So we'll be putting like 2 decades of a point collection, like from 2000s to 2018 into our model. And because of using land covers, a current land cover and a 10-year prior to that, we can get SOC maps for any of those areas between 2000 to 2018, given if we have land covers for area current and the 10-year back. So we'll be using climatic covariables, elevation-based covariables, soil taxonomy, drainage and ecological classes, and soil pH to show types of soils or like inherent soil properties, and the dynamic factor which changes with time are like land cover changes for two different time periods. So our model was based on 1400 points, and we divided our data into training data and test data. And this is how our predictions were compared to the test data. The correlation between predicted values and actual values in the test data was 59%, which shows our model explained the 59% of the variance, and our model was significant. And the important covariables were like mean annual precipitation, elevation, slope, pH aspect. Here I list first 15 important covariables. And this figure really shows how like different covariables and different ranges of them help to, like, if we see it in the range of 36 tons per hectare when the prediction was 36, if the mean annual temperature, if it was 19.4, between 19.4 and 19.8, it actually had a negative effect on soil organic carbon. But like in around the predictions of 59, or like to round it 60 tons per hectare, the mean annual temperature, if it's greater than 19.8, had a huge positive effect on soil organic carbon. So we're actually analyzing our model like uh, to like what factors affect the soil organic carbon most, and the next step would be to make prediction maps for different years and compare them to the available maps which are available for those years. So to summarize, this type of approach, which combine land management and soil type and study its effect on soil organic carbon, is very useful. The more data points will make our model more comprehensive, and and this is very useful for like strategy maker and planners to like monitor soil health and soil organic carbon stocks in soil over time. Thank you. And if you want to know more about my project and have any questions, please email me. Here is my email. Thanks a lot.